now we're going to talk about net charge. So we're going to calculate the net charge of molecules at different pHs. We're going to predict ionization states of molecules when given pHs and pKa's, particularly amino acid molecules, because this is biochemistry, let's get real. We're also going to be able to calculate the isoelectric point of amino acids, because this becomes a really crucial and identifying characteristic of proteins as a whole. So for you, I've drawn the amino acid glycine at its fully protonated state. So this would be what it looks like at pH equals 1. Okay, so what we see here is the amino group. We also see the side chain, which for the amino acid glycine is the same as the proton. So this is actually the only achiral amino acid, and it makes it a great example for this because the side chain is so small, so simple. And then finally, we've got the carboxylic acid portion. Okay, and I've given you two pKa's over here. And looking at the pKa's, you can tell that one of these numbers is lower than the other. This pKa, and remember the lower pKa is more acidic, so this one is more acidic, and this one is more basic. And what we know from the functional groups is that the carboxylic acid likely has the lower pKa. So this proton's pKa is 2.5. And so the amino group's pKa, one of these protons, it doesn't matter which one, they're all equivalent. The pKa of any of these protons is about 9.5. Any one of these protons. Okay. So the acid gives up its proton first, and base, it takes a while because bases are more proton acceptors than proton donors. So keep that in mind. So what does the pKa really mean in terms of pH? So at this particular pH, we can see the protonated state is that the base has all of its protons, the acid has its protons, and the pH is less than the pKa, so everything stays protonated. Nothing has left. That's the rule. When the pH is equal to the pKa, half will be in the protonated form, half will be in the unprotonated form. So remember that from the Henderson-Hasselbalch equation. That when the pH equals pKa, that's the midpoint, and that's when that log part cancels out because we have equal amounts of A minus and HA, and so that makes it the log of 1. Log of 1 is 0. So that's what happens when the pH equals the pKa. When the pH is greater than the pKa, what we get is the unprotonated form. So we've lost all of the protons. So we start in the HA form, and then as the pH increases greater and greater, we lose more and more of this proton. As we lose the proton, it becomes the deprotonated species until all we have left is the deprotonated species. So now I'm going to show you what that looks like on glycine. Okay, so we've got glycine at pH 1. What happens at pH 3, for instance? So now we know that the pKa here is 2.5. So at pH 3, we have now, the pH is greater than the pKa, so it will be completely in the deprotonated form. So we're going to draw that part first. So what does the O look like after that H is gone? It has a negative charge. Nothing else changes. The pKa over here is 9.5. The pH is 3. So here we are at pH equals 3. The pH for this one is less than the pKa, so it stays protonated. exactly the way it is with its positive charge. H, H, H. Okay. And we could draw this again at any pH between 3 and 9.5 and it would still be this species. So then, if we go on and do, say, pH 10. So this pH is greater than the pKa here. pKa here, remember, is 9.5. So now we'll lose this proton. So now the pH that we're looking at is greater than this pKa. We're going to have a deprotonated species. So this N had a positive charge before because it had an extra bond. Now it loses the positive charge when the proton leaves. So now it has a neutral charge. And nothing else changes. This stays deprotonated because its pH is greater than its pKa. Okay, so that's what's going on with the pHs and pKa's. As the pH increases, we start with a protonated state and we end with a deprotonated state based on the pKa. Okay, so now let's do some net charge. So when we started, we had glycine at pH 1. Let's choose a different color. I haven't used green. Okay. So at pH 1, we have a positive charge here, and that's it. So in order to calculate the net charge is the sum of all the positive charges plus the sum of all the negative charges. And so if it's a neutral charge, it just doesn't count. You don't worry about it. So net charge at pH 1, or N dot C, is going to be positive 1 because of this. That's the only charge on this entire molecule. Simple enough. Let's do it again. Now here we are at pH equals 3. So the net charge is going to be all the positive charges, so we've got plus 1, added to all the negative charges, so we've got negative 1. So the net charge here is actually 0. And this is really, really interesting because we have no net charge. This is called the isoelectric point. And this point actually refers to the specific 1 pH at which we finally reach this net charge of 0. So, at which net charge equals 0 for the first time. Because any pH between 3 and say 9.5, we're going to have a net charge of 0. So you can't have, that's like an infinite number of numbers. That's ridiculous. So the first point, the first pH where the net charge is 0 is the isoelectric point. Don't get confused on that. Okay, and then finally net charge. In this pH 10 situation, net charge is the sum of all the positive charges, there aren't any, plus the sum of all the negative charges, so it's negative 1, because the only charge here is this. Okay, so that's how you solve net charges. So now let's calculate the isoelectric point for glycine. Isoelectric point for glycine. What is the point of anything? Haha. What is the point at which the exact pH at which glycine's net charge becomes 0? So the best equation that we can use to do this is the Henderson-Hasselbalch equation, as long as we say that the pH, when all the ions perfectly balance out to 0, is called the PI. So then instead of writing pH equals pKa, we write PI equals pKa plus the log of the deprotonated species over the protonated species. But we have 2 pKa's going on here. We've got pKa of the acid, and we'd have to do the same thing for the base. So NH3. So each one of those, A minus over H plus. And we already know, HA. We already know that at this special pi, they're exactly equal to each other. So the log portion completely drops out. Okay, and then to get the overall pi, we're going to have to add both of these expressions together. So we're going to get 2 pi equals pKa of the acid plus the pKa of the base. So we can then solve for the pi by basically taking the average of the pKa's. COH plus pKa NH3 over 2. So in this instance, it's really stinking easy, right? So we just take the pKa of the acid, 2.5, plus the pKa of the base, 9.5 over 2. We get the pKa. So this expression becomes 12 over 2. So pi is the pH 6 in this instance. Okay, so let's go to a slightly more complicated example. So here we have aspartic acid. You can tell by the side chain, and you'll need to be able to identify all the amino acids eventually. Okay, so we've got the amino group, the acid group, the side chains. Okay, and I've already drawn it all out, identifying the pKa's of the different circled protons immediately before. So the pKa of this proton is 2.1, pKa of the side chain proton is 3.9, pKa of the amino proton is 9.8. Okay, so that's what these red numbers are. Okay, so these are at no specific pH, but you can imagine that. So let's look at the net charges really quick. So the net charge here is +1, here is 0, here is -1, and here is -2. If you can't do that, please speak up during class and we can do more examples. Okay, so we have 3 pKa's, so how are we supposed to take an average in order to find the isoelectric point? The trick to this is you only look at the pKa's that would be in between or immediately next to the isoelectric point. So we can completely ignore, oops, oh, that's funny. So we can completely ignore the contribution of the amino pKa to this equation. So we're going to just look at pKa1 here. We're going to call this 1, 2, and 3. So we're going to look at pKa1 and pKa2 and take the average of those. So this is 2.1 plus 3.9 over 2. So this is 6 over 2. So the pi here is 3.0.